is on the nested subset differential attack, a practical direct attack against LUOV, which forges a signature in 210 minutes. This is work by Jintai Ding, Joshua Deaton, Vishaka, and Boyin Yang, and Joshua will give the talk. Please, Joshua, share your screen and unmute yourself.
Okay.
Sorry, I was not.
Can you hear me and see my screen?
Yes, we can hear you loud and clear.
Cool. All right, so I'll just begin the talk then. So in our paper,
right, can you go into full screen mode?
Wait a second.
I believe it's up at the top under view.
Does that do it, or am I still not? Because I don't know what I look like on your end.
Yes, that's correct.
So is everything good now?
Yes.
Okay, excellent. All right, so in our paper, we introduced a nested subset differential attack, which we call NSDA, against the signature scheme lifted unbalanced oil and vinegar by Bruins et al. NSDA is an improvement to the previous attack, subfield differential attack, SDA, both of which make use of the lifting modification for which LUOV is named. So LUOV is a multivariate polynomial scheme. This means that the public key P is an M tuple of multivariate polynomials over a finite field. And we'll say that we'll have M polynomials and N variables. The private key is a way to compute P inverse, by which we don't necessarily mean it's invertible, but we have a way of finding preimages, but we use that notation. When you're signing the hash of a document, it's just finding one of these preimages. So if Y is the hash of a document, the signature X is just going to be a preimage of Y. The verification process just seeing that Y is indeed the output of X. Now, LUOV is based on the oil and vinegar signature scheme, which was introduced by Padron in 1997. And in that scheme, P was the composition of two maps, F and T. F is quadratic, it's easy to compute F inverse. T is a linear invertible map, and it's used to hide the structure of F. We then see that if those two maps have these properties, we can find preimages, as X is the preimage of Y, can be found by first computing F inverse of Y is W, and then T inverse of W is equal to X. Notice that P is also quadratic, as it's F composed of T, and F is quadratic. I won't go into any details of how oil and vinegar works in here due to time. Now, LUOV takes an oil and vinegar private key over a small field F2, which is the finite field of size 2, and lifts it to an extension field F2 to the R, from which it signs its signatures. This allows more efficient storage of the public and private keys. And that means the public key P of X has coefficients only in F2, so alpha, beta, gamma are in F2, but it will be a map from F2 to the R to the N to F2 to the R to the M. Now, in our attacks, SDA and NSDA, we rely on the quotient ring representation of finite fields, which means if I take a base field F2 and an extension field F to the R, I can represent F to the R by the following quotient ring, where D divides R, and G of T is an irreducible polynomial of degree S is equal to R divided by D. Elements in F to the R can be represented by degree R divided by D minus 1 polynomials in this polynomial ring here. Now, it's more efficient to solve a quadratic system over that intermediary field than over the extension. So the goal of both SDA and NSDA is to turn the problem of solving over F to the R to solving over F to the D. In the original SDA attack, we looked at transforming the public key by adding a random differentiable X prime and solving over F Q to the D. That should be a 2 instead of a Q. So we defined our new map, P tilde of X bar is equal to P of X bar plus X prime. And this separated out linear terms for all powers of t, but kept the quadratic terms contained at t to the power of 0 is equal to 1. This made the system easier to solve. What we did is we decomposed the message y into the following sum. Each of these are going to be vectors in the vector space over the intermediary field. And we solved for the higher powers of t using the linear terms first. And that's because p tilde of x bar takes the following shape, where we have these quadratic terms next to t to the power of 0 and a bunch of linear terms for all the other powers of t. So we solve for the higher powers of t using the linear terms first, and then at the end solve for the quadratic terms. And this is easier, provided it's possible to do, which means do we have sufficiently many variables. In response, the authors of LUV proposed new parameters, which in particular made the degree of the extension field prime, which protects against SDA. There are too many linear equations to solve. Here's a table of the 6 new parameter sets. Our attack in SDA is against the 3 cases when R is equal to 7, and it breaks these completely. So R is prime, we are attacking these parameters here. We'll note that our attack in SDA does not defeat the other 3 parameter sets, but only the ones when R is equal to 7. So throughout here, we're going to have R is equal to 7. We will construct a signature for the message y piece by piece using differentials. However, instead of choosing the differentials randomly like in SDA, we instead solve for them one after the other. For R is equal to 7, this can be done in 4 steps. For our attack to be efficient, we want to always solve no more than m quadratic equations over f2 with at least as many variables as equations. And we have to solve over f2 because there's no other intermediate field to the d, because d can only be 1 because R is prime. Throughout, x bar will be an indeterminate point and f2 to the n. And we'll just introduce some notation here quickly, and that we'll always truncate the powers of t that we're dealing with, which means if I have just an element of the finite field, I raise this bar s over top of it, I only go to the powers of s. And it's similarly defined for polynomials and systems of polynomials. So step 1 of our attack is to look at that 0 truncation of p. And that is just going to be, by definition, the original quadratic polynomials, except now we're only considering them over f2. And we just find the solution to the system over f2. Second, we take that solution over f2 and we add an unknown differential x bar t. And when you do the arithmetic, you'll get the original y's that you solved for beforehand, plus some linear terms multiplied to t to the power of 1. And these are easy to solve, so we're going to let A1 be a solution to that linear system. The third step is basically exactly the same, except now we're adding a new differential x bar t squared. And this will get us linear terms for the t to the power of 2. We again let A2 be a solution to that system. And then finally, we just look at the system completely using this differential here, and we'll have 3 terms for t to the power of 3, t to the power of 4, t to the power of 5, which are linear, and terms which are quadratic at t to the power of 6, which is r minus 1, which is the highest power of t for f2 to the 7 to be considered. We find the solutions for S for the linear system first, and then we attempt to solve the quadratic system over that solution set. And if that is possible, we will then have a signature for our message y. The complexity for the level 1 parameter set is actually low enough that we were able to perform a practical attack against it. We ran an experimental attack against a public key with level 1 parameters, and we were able to forge a signature in 210 minutes. For full details, please refer to our paper. Thanks, and we'd like to say our appreciation for both the CAF Fund, NIST, and the NSF.
Thank you very much. Are there any questions for Joshua here in the room? Are there any questions on online? I'm not checking them. Okay. If there's no other questions, I can ask one question. So so you're attacking this lifting mechanism, right?
Mm-hmm.
It's present in all parameters of this LUOV. So how come that? Does your attack not at all give any improvement for the parameters that you say you don't defeat, or is the improvement just not significant enough?
I should probably share my screen again just to show you. It does not, because as we're adding more and more differentials, we get more and more linear terms for more powers of t. So like for r is equal to 47, we would just have too many linear equations to then solve over the final quadratic equation. So
okay.
Does that answer the question, or should I share my screen again?
No, I think that answers the question. Thanks.
There is also a question in Zoom chat.
Okay, can you read it out?
Sure. This is from Alexei Udovenko. I'm sorry if I mispronounced that. And it is, could intermediate size constants help, or is it futile?
I'm not for sure what he means by the question.
Perhaps
okay.
Alexei could unmute themselves. Or not.
Okay. In that case, I think it's time to thank Josh one more time. And we are moving on to the next speaker. One second. Sorry. How do I do this? This is, which one is yours? This one, right? Can I not go back to Zoom? Like this? Oh, okay. Is it just, I think I do need to just share the screen. Okay. And now. Okay.
I believe if you go to slideshow.
Yeah, there we go. Okay. Now we should be good. So the next talk is by Vart Buildens, and it's about improved cryptanalysis of UOV and Rainbow.
So yeah, hello everybody. So yeah, I'll be talking about oil and vinegar and rainbow. So what's that? Those are two multivariate signature schemes. The first one, oil and vinegar, is the oldest one. It's invented in 1997 by Paterin. And in the following years, there was some cryptanalysis results, but then quickly those attacks dried up, and there have not really been any real improvements since then. And the good thing about oil and vinegar is that it has very small signatures and it's very fast. But the main drawback is that the public keys can be quite large, for example, 60 kilobytes for NIST security level 1. And on the right-hand side, we have Rainbow, which is basically multiple layers of oil and vinegar on top of each other. It was invented in 2005 by Ding and Schmidt. And yeah, it's a bit more complicated, but also has a little bit smaller signatures. And importantly, it's one of the finalists of the NIST post-quantum competition. And in my work, the main contribution, I would say, is that I simplified the exposition of oil and vinegar and rainbow. And because of this, this better understanding of the scheme, I was able to find some new, more efficient key recovery attacks. So yeah, these oil and vinegar and rainbow are based on multivariate trapdoors. So particularly that means your public key will be a multivariate quadratic map that looks random. So we believe that it's hard to sample pre-images for this function. But map is actually not random. There is some secret information. And if you know this information, then you can efficiently sample pre-images. And a signature is then just like an input S, such that P of S is the hash of your message, where you use some hash function that outputs elements in the codomain of your function. So yeah, the only thing you need to know to understand Oil and Vinegar and Rainbow is how these trapdoors work. And yeah, if you look at a typical Rainbow paper, for example, then you will have an explanation like this. And yeah, if your brain works like mine, then you'll have a hard time understanding this. And even if you convince yourself that this is a trapdoor, then you still don't have the feeling that you really understand what's going on. So that's what we're going to try to solve in the next few minutes. But before I explain Rainbow, I'll explain Oil and Vinegar because it's a bit more simple. So the trapdoor is really simple. So it's just a linear subspace of your input space of dimension m, where m is the dimension of your output space, such that P vanishes on O. So that means for every vector O in this space O, we have that P of O is equal to 0. And it turns out that if you know such a space, then sampling a pre-image is actually very easy. So how do you do this? You start by just picking a random input, which of course will not be a pre-image, but then you can solve for some correction term in this oil space such that, so that P of V plus O is your target. And you can do this because you can write this P of V plus O as like this. So this is always the case for a quadratic function. If you have P of a sum, then you can write it as P of the first term plus P of the second term plus something that's linear in V and O. And this something we call the differential of P. And so in our case, we can solve this efficiently because like P of V is just something fixed because we fixed the choice of V. P of O is 0 because P vanishes on O. And then we're left with something that's linear in O. So this whole equation is just a system of m linear equations in m variables. So you can just use Gaussian elimination to find a solution. And in an unlikely event that there is no solution, you just go back to step 1 and you try again with a different vector V, right? And then you just output V plus O. So that's in a nutshell how Oil and Vinegar works. Rainbow is a little bit more complicated. So instead of one space O, you now have this chain of spaces from O1 up to OK, where K is some integer. And you also have a chain of spaces in your output space, going from W1 up to WK minus 1. And we wanted our trapdoor map P behaves in a nice way on these two chains. So in particular, it sends O1 to W1, O2 to W2, and so on. And finally, it sends OK to the 0 vector. So it vanishes on OK. So you see that this is just a generalization of Oil and Vinegar. If you put K equals 1, then you get just the Oil and Vinegar structure. But on top of this property, we also demand something else, which involves this differential that I defined earlier. We want that for every vector x, if you plug it into this differential, then you get some linear map that maps OI into WI minus 1. So if you have these two properties, then it turns out you can sample pre-images. And the strategy is basically multiple steps of this Oil and Vinegar ID. So you start with a random vector in here, and then you solve for a correction term in O1, such that you correct pre-image up to some vector in W1, and then you're going to solve for a correction term in O2, such that you correct up to a vector in W2, and so you go back and forth until finally you solve for a correction term in OK, such that you have a correct pre-image. Right, so and each of these steps is just solving a system of linear equations, so you can do this very efficiently. So yeah, that's how Rainbow works, and this is, I believe, a much nicer explanation than the standard explanation. And this allowed me to find some more efficient attacks. I found two key recovery attacks. The first one I called the intersection attack, and it applies to both UOV and Rainbow. And the second one is more efficient, but it only applies to Rainbow. And I don't have time to explain how the attacks work here, but it's fairly straightforward. So if you're interested, please watch the video or read the paper. So for now, I'll just focus on the complexity of the attacks for the parameters that were submitted to the NIST competition. So yeah, in this table, the first two columns are the two new attacks. And you see that they're always better than the previously best known attacks. And in particular, this min rank attack is the most efficient. So for the NIST security level 1 parameters, we improve on the best known attacks by 20 bits of security. For yeah, the third one, it's 40 bits, and for security level 5, it's 55 bits. So yeah, it's a significant reduction in the security. So yeah, that's it. So in conclusion, in this paper, I give this new simplified explanation of how oil and vinegar and rainbow work. And using this new insight, I was able to find new attacks that significantly reduce the security of rainbow. So yeah, that's it. Thank you very much.
Thank you. Are there any questions for Ward? You need to switch on the microphone.
Thanks for the talk. I believe the authors of Rainbow have acknowledged the attacks, but said that they don't need to change parameters. Is this correct? What's your take on this?
Yeah, so they claim indeed that it's not necessary to change their parameters, but they had to change to a new model to estimate their complexity. So previously they only looked at the gate complexity, so how many gates you need for the attack. And now they switched to a model where you also take into account the cost of accessing memory. And yeah, if you take this into account, then of course the costs of the attacks are larger. So in that sense, you can make an argument that is still secure, but that doesn't change the fact that you lose 20 bits of security or 40 bits or 55 bits. So yeah, whether it's still secure or not, that's kind of up to how you interpret the NIST rules. So that's not for me to say, but yeah, the important thing is that however you measure the security has gone down by at least 20 bits.
Thank you very much.
Is there one more quick question? Okay, if not, then let's thank Ward again. Okay, the next speaker is online, I believe.
Yeah, let me try to share my screen.
Yes, that would be great. Yes, so then the next talk is, there we go. Okay, great. The next talk is by Itai Dinour on cryptanalytic applications of the polynomial method for solving multivariate equation systems over GF2.
Okay, thank you very much for the introduction. So in this work, I will consider the problem of solving polynomial systems over F2, where the input is consists of m polynomials in n variables, where each polynomial has a bounded degree of d, which is typically small, like d equals 2. And the goal is to find a solution to the equation system, which is basically common zero for all of the polynomials. Now, the problem is known to be NP hard, even for a quadratic system, and it is very difficult in practice as well. It's a central problem in computer science and specifically in cryptography. Now, standard techniques for solving polynomial systems are based on Grobner bases, and they are typically heuristic. However, in 2017, Lokshtanov et al. Presented the first worst-case algorithm with exponential speedup over brute force. Now, this algorithm is based on a so-called polynomial method in circuit complexity, which was originally introduced for proving circuit lower bounds. Now, here is a high-level overview of a few related works that include optimized exhaustive search and Grosvenor basis related algorithms. Now, the polynomial method algorithms have been, since their introduction, they have been improved. And now they actually give the best known asymptotic complexity for solving polynomial systems. However, in this work, I will be mainly interested in the concrete or non-asymptotic complexity for solving F2 equations. And this is relevant essentially for choosing parameters of concrete cryptosystems. This is the main motivation. Unfortunately, close analysis of the polynomial method algorithm reveals that the constants behind these asymptotic formulas are quite large, and the algorithms have no concrete cryptographic relevance. So in this work, what I do basically is present a polynomial method algorithm, which is concretely efficient for solving F2 equations. Unfortunately, there is a caveat because it requires a significant amount of memory, and this is an obstacle for obtaining a fast implementation of the algorithm in practice. However, in terms of time complexity, it seems to be the best known algorithm for a wide range of parameters. And this slide gives numbers for some concrete instances, as you can see. And perhaps a bit surprisingly, the algorithm beats brute force, at least in terms of time complexity, for a relatively large degree, say of d equals 4, for problem sizes that are actually relevant to cryptography. So the main application of the algorithm is in cryptanalysis of PICNIC, which is an alternate third-round candidate in NIST post-quantum standardization project. And it essentially shows that some instances of PICNIC 3 do not achieve their claimed security level. And you can see this from this table. Essentially, these two larger instances do not achieve their claimed complexity level, at least in terms of time complexity. Okay, so let me give a very brief overview of the techniques. I don't have much time, but I'll give you just a flavor. So I'm given a polynomial system E. I'm going to define a polynomial f that a single polynomial f that evaluates to 1 only on solutions to E. Unfortunately, if you define it correctly, the polynomial, the degree of the polynomial is too high to be manipulated efficiently. Therefore, what polynomial method algorithms do is define a probabilistic polynomial f tilde that on one hand approximates this original polynomial f, and on the other hand has lower degree, so it can be manipulated efficiently by algorithms. So previous work essentially exploited the low degree of f tilde to compute the parity of the number of solutions to the equation systems, and from this you can actually solve E, the equation system. However, this required working with many probabilistic polynomials and was inefficient, at least in terms of concrete complexity. So one of the contributions of this work is a more direct and efficient way of solving the equation systems, the equation system from parity computations. So let me briefly conclude. So in this work, I devised a concretely efficient polynomial method algorithm for solving F2 equations. In the paper, there are additional contributions, such as reducing the memory complexity of standard implementation of the algorithm by an exponential factor, although it still remains high. Another contribution is optimizing the algorithm for concrete crypto systems. And now there are several open problems. One of them is to optimize the algorithm for over-defined systems in which you have many more equations than variables. And of course, another open problem is to obtain a fast implementation of the algorithm in practice. So thank you very much for your attention.
Thanks, Itai. Okay, I can already see some people are lining up for questions.
Hi, thank you for the talk. I was wondering, does the new algorithm include any sub-steps doing exhaustive search that could imply a quantum algorithm by just Groverizing some smaller component?
Yes, I think you can speed it up with my feeling. I haven't done this computation formally, but I think some steps can be optimized, and I think there is a hope here to get also faster algorithm using on a quantum computer. But like I said, I haven't checked the details, so not exactly sure about that.
Thank you.
Okay, so thanks for the talk. I had a rather technical question, like directly concerning the paper. So if I remember correctly, you were defining like N1 parity counting functions, that from the first one, you were getting the values of Y, so the N minus M1 bits of the solution, and then you were evaluating the rest on the value that you got for Y in order to get the rest of the bits, true? So what I was wondering was that, can't you do like some linear mixing of the variables in the beginning, and instead of like doing N1 parity countings, just do the first one like multiple times and try to like solve like do some Gaussian elimination or something to get all the bits, because M minus M1 I remember was like way bigger than M1.
No, I think you cannot. Maybe you can do some minor tweaks here to improve the complexity, but I don't quite see how you can kind of improve this in a substantial way. I mean, you can do some linear algebra tricks and maybe maybe obtain slightly better concrete complexity in some cases, but I don't really see what you mean by substantially reducing the N minus N1 term here. Maybe you can send me a concrete proposal by email and I look it up, but
okay. Sure.
I don't quite see how to do it.
And another question. So I was wondering that if I remember, the attack only worked for like the full S-box layer instances of low MC, right? So I was wondering if there
it's
is
efficient. You can try to apply it for a partial S-box, but the partial S-box versions have more rounds, so the algebraic degree is larger, and therefore the attacks will be much less efficient.
Yes, true. I was wondering if there is a trick to like have like introduce more equations, but with lower degrees somehow, that would somehow be, make it possible.
You can introduce more variables, that I can see how you can do, but then of course the complexity will increase proportionally, and therefore I don't see how the algorithm would be valuable in this case. I mean, if you have a suggestion, I'll be happy to hear it, but I currently don't see how to do this.
Thank you.
Okay, I think we should probably move on to the next speaker. So let's thank Itai one more time. So the next talk is about round optimal blind signatures in the plane model from classical and quantum standard assumptions. And this is work by Shuichi Katsumata, Ryo Nishimaki, Shota Yamada, and Takashi Yamakawa. And Ryo Nishimaki is giving the talk.
Can you hear me?
Yes, loud and clear.
Okay, I'm going. Thank you for the introduction. I'm going to talk about the blind signature. This is a joint work with Shuichi Katsumata, Shota Yamada from ICE, and Takashi Yamakawa from NTT. This is our result. We proposed round optimal blind signature protocol that has 3 desirable properties. First, our protocol does not rely on any trusted setup assumption. And second, our protocol is based on standard classical and quantum assumption. So our talk was assigned to post-quantum cryptography, but actually our protocol is not post-quantum secure because we use standard classical assumptions. And our protocol does not rely on complexity leveraging. Okay. So first, let me review the notion of blind signature. This is digital analog of sealed envelope with carbon copy seed. There is a signer and user. A user has a message, and the sender, the user, send a message, put a message into the sealed envelope and send it to the signer. The signer signs the message without opening the sealed envelope, because the envelope with carbon copy seed, if the signer sign on the envelope, then the seed has the signature. So next, the user open the sealed envelope and get a signed message. This is blind signature. And there are many applications of blind signature. But in particular, blind signature is a crucial building block of privacy-preserving crypto system, such as eCash, e-voting, anonymous credentials, direct anonymous attestation, and more. This is the state of the art of round optimal blind signature. Most of them rely on some trusted setup assumption, such as common reference string model or random walk model. Fisher-Bauer et al. And their follow-up works proposed the round optimal blind signatures without trusted set assumption by using interactive assumptions. So those protocols are based on strong assumptions. In fact, round optimal blind signatures without trusted setup from standard assumption is impossible under some conditions. Gag et al. Overcome this impossibility result by using complexity leveraging. Their protocol uses complexity leveraging twice. Gag and Gupta also presented the round optimal blind signature protocol with by using complexity leveraging. This protocol used only once, but notable feature of this protocol is the protocol heavily rely on the algebraic structure of pairings. So our blind signature is the first round optimal blind signature without trusted setup assumption from standard assumptions, and our protocol doesn't rely on complexity leveraging. Our protocol is based on blind signature protocol by Gag et al. The protocol is as follows: the signer generate a key pair of standard signature, and the signer and the user run the secure function evaluation protocol, and the user gets a signature for the message M, and the signer gets nothing. So we can the user can obtain the signature for M without revealing message M. However, the signer might deviate from the protocol, so we need to use zero knowledge protocol to force the signer follow the protocol. So by using zero knowledge, we can prove the security of this blind signature protocol. Blindness follows from zero knowledge, soundness of zero knowledge protocol, and the receiver security of secure function evaluation. Unforgeability follows from zero knowledge and the sender security of secure function evaluation. However, their protocol need to use complexity leveraging to prove these two properties. Our basic idea is as follows. using complexity leveraging need a super polynomially secure cryptography. We replaced super polynomially secure cryptography with quantumly secure one by using quantum power for super polynomial reduction. This idea was inspired by the work Kalai and Krana. However, there is one issue. The protocol by Gag et al. Used complexity leveraging technique twice. The quantum technique works only for complexity leveraging only once. So we cannot simply use the technique by Kalai and Krana. In fact, the protocol by Garg and Gupta use complexity leveraging only once. So we might use the quantum technique for their protocol. However, their round optimal blind signature protocol is not compatible with quantum simulation due to heavy use of algebraic structure of closed high-proof system. To solve the problem, we introduced the notion of a blind signature conforming zero knowledge. This is zero knowledge protocol, only two-move zero knowledge protocol. And the prover can register possibly ill-formed public keys because we use this zero knowledge argument for the building block of blind signature. The prover is the user of the blind signature. So the prover can register public key. And in this zero knowledge, the simulator is quantum polynomial time simulator. So the simulator can break classically secure crypto system in reductions. So this can be used instead of complexity leveraging. To solve the complexity leveraging twice problem, we use many techniques. One of the key tools is public key encryption with invalid key certifiability. We can prove that a public key is ill-formed for Regge public key crypto system by using a proof system by Aharonov and Regge. We carefully combined this public key encryption with lossy encryption and that, so we can overcome the complexity leveraging problem. Please see the video or paper of the detail. This is a summary. We achieved the round optimal blind signature protocol by using standard classical and quantum assumptions. This protocol does not rely on any trusted setup, and we don't use complexity leveraging technique. We introduced many interesting techniques for this protocol. That's it. Thank you.
Thank you for the talk. I'm not sure whether we have maybe time for one quick question. Maybe I will just take the liberty to ask one. So basically, you need your honest, some parts of your protocol to be quantum secure, and then you use quantum simulation to break some classical secure part. So basically, if you wanted quantum secure post-quantum security for the whole protocol, your technique would not be applicable, right?
Yeah, our techniques does not work for post-quantum secure crypto system. I mean, our blind signature protocol is not post-quantum secure because
right, and basically yeah. the technique is fundamentally not suited for that, right? Because you would need the quantum breakable things. Okay, yeah. Thanks. Okay, I think we should move on to the next speaker. Thanks, Rio.
Thank you.
Sorry. No, this was not what I wanted. Okay. So can you open your presentation? Which one is it? So, okay. There we go. Okay, so the next talk will be by Amit Agarwal, and it will be on post-quantum secure multi-party computation in constant rounds.
You'll actually need to switch around the display settings. So in the upper left, I believe, because we're seeing the presenter mode remotely.
Is
Yeah.
it this?
Yeah, swap presenter view.
Okay.
Perfect. Thank you.
Okay. This does not work because now the audience in the room sees the presenter mode. 1 second.
Oh, great. Okay.
So what can we do?
As you all may have gathered, we are still working out kinks.
Let me try and share this. How does it look now? Online?
It's still loading, so I think give it a second. I'm hoping it's just a lag.
I don't see full screen.
I don't
Okay.
either. It may also be under display settings, that same menu. There was another option that I believe said duplicate slideshow. That may also be what you need to click. I'm not sure.
Oh, I see. Okay, thanks.
Sure.
So.
Thanks for your patience, everyone, from the disembodied voice in the cloud.
There we go. Sorry for the delay.
Perfect.
Hi, everyone. Today I'll be talking about my work on post-quantum MPC in constant rounds. And this is joint work with James Bartosek, Vipul Goyal, Dakshita Khurana, and Julia Manavalta. And I would like to thank James for letting me use his slides. So let me first start with the setting of MPC, where we have a bunch of parties, each with their private inputs, and they want to compute some public circuit on their private inputs. And the adversary might corrupt some subset of these parties. And the goal is that the adversary shouldn't learn anything about the inputs of honest parties, apart from what it can learn from the output of the functionality. And the setting that we are interested in is quantum polynomial time adversaries with malicious behavior, dishonest majority, and static corruptions. We note that in the two-party setting, there has been some prior work to solve this problem in the plain model, but in the multi-party setting, this has been largely unexplored. And the main challenge lies in working against quantum polynomial time adversaries because of this no cloning theorem, which states that given an arbitrary quantum state, you cannot make two copies of it. And this creates challenges in simulation techniques. So our high-level approach is the following. So we note that there are already existing constant round classical MPC protocols secure against classical adversaries with a trusted setup. And furthermore, if you instantiate the underlying primitives used in these protocols with their post-quantum analogs, then what you get is a post-quantum secure MPC, but with a trusted setup. And this trusted setup is a common random string. And what happens is that the simulator in the security proof programs the CRS, and henceforth, once the programming is done, the simulation is entirely straight line. So we note that it suffices to build a constant round fully simulatable coin flipping protocol, which helps us instantiate the common random string. So let me describe the setting of fully simulatable coin tossing. So we have a functionality which just returns a random string R to all parties. And a natural protocol template for realizing this functionality is the following. So each party commits samples some random string Ri and sends a commitment to it to all other parties. Then each party broadcasts the opening values to these commitments and proves in zero knowledge that this opening value is consistent with their commitment. And if all the proofs verify, each party outputs the XOR of all the open values. Now in the constant round setting, we need this first round to be a multi-party constant round extractable commitment. And the zero knowledge proofs should also be multi-party constant round zero knowledge proofs. And the main challenge lies in constructing this multi-party constant round extractable commitment in the quantum setting against quantum adversaries. And once we have that, we can get multi-party constant round zero knowledge proofs from the extractable commitments. So if we were just interested in two-party setting, there have been some prior works which show how you can get a non-rewinding, no cloning extraction technique. And this is known in the literature as a homomorphic trapdoor paradigm. So here we have a committer and a receiver, and we want to create an extractable commitment where extractor doesn't rewind that visit. So let me give you a sketch of how the protocol looks like. So the committer samples a FHE key pair, a trapdoor, and a lock value. So this protocol, by the way, makes use of FHE and the compute and compare obfuscation. So just keep that in mind. So this is the first step. And then as a second step, the committer computes an encryption of the trapdoor, FHE encryption of the trapdoor. And then it prepares this very special compute and compare program, which has the FHE decryption circuit hard-coded within it and a target lock value. And the output is the secret key and the message. So if inside this program, so if you feed an encrypted trapdoor to encrypted lock to this compute and compare program, then what you get as the output is the message and secret key. Otherwise, you get bot. So committer obfuscates this program and sends over the triplet consisting of public key, encrypted trapdoor, and obfuscated program to the receiver. Then in the second round, receiver has to take a guess at what the trapdoor is. And if the guess is correct, the committer returns the lock, otherwise it returns bot. So naturally, a real-world receiver cannot guess what the trapdoor is in the second round, and therefore the lock will be hidden from its view, and hence the compute and compare program will hide the message. Now, an extractor which has non-black box access. So by the way, this simulation technique makes use of non-black box technique. So we assume that the extractor has access to the code of the adversary. So an extractor which has non-black box access to the committer can get the same triplet. Like a real world receiver, it cannot guess at what the trapdoor is, but what it can do is run this fourth step of the committer under the hood of FHE. So it can just supply the encrypted trapdoor under the hood of FHE and evaluate this fourth round and get out the third round message, which is indeed the encrypted log, because under the hood of FHE, the guess was indeed correct. And once it has that, it can feed it into the compute and compare program to get out the secret key and the message. And now it has successfully extracted the message. Now we can try extending this technique to the multi-party setting where we have multiple committers, which we are interested in, but it runs into some issues. So the extractor gets two triplets of public key, encrypted trapdoor, and the compute and compare program. But it's unclear how to evaluate this guessing step in one go. So the issue is basically that the extractor has only one shot to evaluate the adversary. And in one shot, it has to do this FHE evaluation. But the trapdoors that the extractor has are encrypted under independently generated public keys, PK1, PK2. So it's unclear how to do this homomorphic evaluation in one shot. So we note that there is this notion of multi-key FHE in the literature, which is a natural generalization of single client FHE. Now here we have multiple clients, each with their public secret key pairs and their inputs. They can encrypt these inputs using their public key, send it to the server. Server can then do a homomorphic evaluation of the ciphertext under the joint public key of all the clients, and then send out ciphertext to all these parties. These clients using the secret key can locally decrypt this ciphertext and compute what is known as a partial decryption. Now, the crucial property is that these partial decryptions add up to the output of the actual function. So in our paper, since our adversary is quantum, we need a multi-key FHE scheme which works for quantum circuits. And we construct that by combining single key FHE schemes for quantum circuits and multi-key FHE schemes for classical circuits, which are already present in the literature. We combine these two to create multi-key FHE scheme for evaluating quantum circuits. So once we have this tool, we directly plug this tool in our FHE evaluation step. Now we can just replace this FHE evaluation with a multi-key FHE evaluation, supporting evaluation of quantum circuits, and feed in the 2 encrypted trapdoors. So now what we have is encrypted locks. So now we are in a better position than before, but the problem is not completely solved because the encrypted locks are under joint public keys. And to make use of the compute and compare program, we have to peel off the layers of public key. I won't be able to go into the details of how we do that peeling, but we make use of the spooky property that I mentioned earlier, that partial decryptions add up to the output of the function, to peel off the public key layers and then feed them into the obfuscated program to finally get out the secret keys, both secret keys and both messages M1, M2. So I'll just not go over the slide in the interest of time. Yeah, so this helps us finally construct this constant round multi-party extractable commitment secure against quantum adversaries. And using existing techniques, we can directly use extractable commitments to construct constant round zero knowledge proofs. So we note that just having extractable commitments doesn't solve the entire issue because an adversary might be able to maul an extractable commitment. So what we end up also needing is non-malleable commitments, which are constant round. So in this paper, we combine the erasure channel based approach of constructing constant round commitments with tag amplification technique to construct post-quantum constant round non-malleable commitments. And we plug this into our final coin tossing protocol to ensure non-malleability. So our final results look something like the following. So we show that there exists a constant round classical MPC protocol. So there is no quantum communication happening inside the protocol, which is secure against quantum polynomial time adversaries in the plane model, assuming an LWE-based circular security assumption. And this assumption is used in order to create the quantum multi-key FHE scheme that I talked about earlier. And we use that in turn to create constant round parallel extractable commitment, and then constant round parallel zero knowledge proof, which are both secure against quantum adversaries. The second assumption that we rely on is a mildly super polynomial hardness of LWE. And we use that to create post-quantum constant round non-malleable commitments. Thanks for listening.
Thank you. I think we have time for one question. Is there any questions online? Otherwise, maybe I can ask one question. So, sorry if it's not about your work, but something you use as a component. So, how exactly enters the sub-exponential hardness of LWE in your in the protocol? So, how do you make use of it?
So we assume super polynomial hardness, super polynomial modulus noise. Are you referring to this last assumption?
Yeah, the mildly super polynomial hardness.
So we need this to create constant round non-malleable commitments. So basically, we create multiple hardness levels to instantiate this erasure channel based approach. So in this work by Khurana and Sahai, so basically what happens is you create an erasure channel between each pair of pairs, and this erasure channel is created using a secure function evaluation. And by having different levels of security of each secure function evaluation, you have different erasure channel security levels, and that helps you create a non-malleability between each communication channel.
Okay.
And yeah, so that is needed in order to create these multiple hardness levels.
Thanks.
Yeah.
Okay. I think we should wrap up. Let's thank all the speakers of this session one more time.